Computer. Great. Take that away. Okay, so welcome everybody. So this is the first week of functional ingredients. So this week in general culinology, we're going to talk about pH in relationship to this general culinology. In food science, we're really going to go into it and look at the difference between pH and titration and all this other kind of stuff. So but for here, we're just going to look at a more of a general kind of overview. I was looking at the quiz and I noticed I happened to slip in a couple of more advanced questions. Some of you got them right, some of you didn't. So if you didn't get them right, know that we will cover that later. So don't feel too bad. One of the questions from the discussion was about polar and non-polar molecules. So I told you I always read the discussion, and if you put a question in there, that's where you get my feedback. So that was one. So what is a polar molecule? So a polar molecule is something that has charges, right? Positive and negative charges. So that's what a polar molecule is. And so we can look at water right here. Water. We could look at water. This molecule right here is water. And water is H2O. So it's a hydrogen. Oh, this is an acid. This is water. This is one. Oops. Let's try this again. This down here is water. H2O. So because the oxygen is really large and the hydrogens are really small, the hydrogens tend to have a positive charge and the oxygen a negative charge. And so that makes it polar. It has positive and negative signs. We look at an acid, this one right here, this is acetic acid right here. This is carbon here, double bond oxygen, and then a oxygen and a hydrogen. And this hydrogen tends to dissociate from the main molecule. And so when it does that, it takes its proton, but not its electron with it. So the hydrogen now has a positive charge and the acid has a negative charge. Is that sort of clear?
Yes, that helps.
That helps. So now if we look at a fatty acid right here, this is a fatty acid. Remember, a fatty acid is a long chain of carbon molecules. There are no charges on here, right? So this is the part that connects to the backbone, the glycerol molecule. So this disappears, and all of this has just fully engulfed with hydrogens, and there are no electrical charges. So this is non-polar, right? So if we have vinegar, acid over here, and oil over here, they don't mix, right? So because this is polar and this is non-polar, they separate from each other. They don't interact with each other. Does that make sense?
Yes.
Oh, good. Okay. Well, we'll be talking about this a lot more when we get into food science and we begin to look at the molecules in general. But ask a couple of people ask. So there we go.
Jill?
Yeah.
What happens with a polar and a non-polar when they're put into an emulsification?
So then we have to add a third ingredient. a third ingredient, an emulsifier, or a tween, sometimes called a tween, or so it is something that is polar on one side and non-polar on the other.
Got
So
it.
when we looked at the emulsion, right, we had to add emulsifiers. So we think about mayonnaise, we add lecithin, egg yolk, right? But there's a lot of other additives that also work as emulsifiers. Like when you make a vinaigrette and you add a little bit of powdered mustard or a little mustard to it, the mustard also has a kind of a gum in there that acts as a bit of an emulsifier as well. It's not a very strong one, right? But it's there. Okay. So I see Helen joined, so I want to make sure to give you credit for being here. And welcome, welcome. And the last person, oh, John has come back. Okay. Hi, John. Welcome back.
Hello.
Helen, were you here last week?
Yes, I
I
was.
was.
You were. Okay. I missed you.
Oh, well, let me make sure then.
No, I was here.
I know John was here. Yeah. I had you down, but I didn't have Helen. I missed that. Okay, so if we look at from a previous class, somebody asked what a protein was, and a protein is an amine. It's the suffix amine, and it means it has an amino group. So if we look at, this is the chemical structure for protein. So it has a central carbon and it has nitrogen. And when we talk about protein, we say protein is special because it contains nitrogen. And then it has an acid group on the other side. And this is like a choo-choo train with hooks on either end. So the nitrogen connects with the acid, connects with the, like with a carbon, with a nitrogen, with an acid, with a carbon, and it makes this long chain. And that long chain is what you inherit from, your DNA. That's what we get from our DNA. And then each one of these, this is the same in all proteins. This is the side chain. So we talked about amino acids before. So this can be any one of those 21 different amino acids. And bringing in polar and non-polar, some of the amino acids are positive charge, some are negative charge, and some are non-polar. So different, you don't need to know which ones, but that's why protein works as a buffer, because some of the amino acids are positive and some are negative. Some are polar, positive and negative. So I just thought I'd leave that there from the last time. Take away my squiggles. So it's called an amine because of the amine for the nitrogen. And if we think back to carbohydrates and to lipids, they do not contain nitrogen. They're carbon, hydrogen, and oxygen. And protein is carbon, hydrogen, oxygen, and nitrogen. So without going over this again, the meat color, did anybody have any questions left over from last week about myoglobin, oxymyoglobin, and metmyoglobin? No, did I talk about it enough that you can remember which is which? Right? Good. Okay. Our previous student, Austin, said, if you want to know more about muscle function, he found this website. So if you want to, because I only briefly went over muscle function. So if you want to know more from him. Moving on to what we're going to cover this week. If there are no more questions from last week. No. Okay. Oh, I see there's a chat going on, which I haven't been paid to. Oh, it's from John. Okay. But you got it working, John.
You can see me because I can't see me.
Oh, I don't see you either. Wait a minute. All I see Oh, I see you.
Do you?
I
Okay,
see
well,
you.
I don't see me, so that's okay, as long as you know I'm here.
Yeah, you're here. I'm not worried. Okay. Um, so functional ingredients. For one thing, we're going to cover these a lot more in food science, but just doing a general thing. So it says discuss the functional properties of common food additives. And today we're going to look at acidulants, alkalis, buffers, and pH adjusting ingredients. And we'll look at some other things next week. And the functional properties of water, salt, and food additives. We'll look at those a little bit. We already did emulsions. So as we've talked about many times before, functional properties. So this is a list of the functional properties that food additives can be used to, that they can give, I guess, to food, right? So I think I won't go through that list unless there's one you have a question about. The properties of water, salt, and food additives. So first of all, water is considered the universal solvent. So that means it dissolves almost everything. But as we said, only polar things. It'll only dissolve polar things because water is polar, right? But that's why we use water for cleaning and, and for dissolving substances. The most important for us characteristic or functional property of water is water activity. So water activity is different from the amount of free water available. Total free water is what you get if you dry it, right? You have your food, you put it in one of those drying things, a dehydrator, and you dry it. All that water that evaporates, that's free water. But water activity is different than that. So water activity, the easiest way to talk about water activity is that's water that's available for chemical reaction or actually for microbial reactions. So that's what, and it is, so it's the water that's available to react with or attach itself to another material. So the higher the water activity, the increase the rate of food spoilage. Right? So the higher the water activity, the increase the rate of food spoilage. But that's not just all that happens. If we look at this diagram down here, if we look at water activity across the bottom and moisture content, reaction rates, reaction rate of the top and water activity across the bottom. If we start down here with really, really dry foods down here, you can see that the water activity is really low, the moisture content is really low, and enzyme, mold growth, yeast growth, bacteria are not existent down here. They're zero. But the one thing that happens with dry food is that lipid oxidation. So you can see that with a really dry food, rancidity is more likely to happen. And that makes sense to us because if we think about potato chips, right? Potato chips are really dry and they go rancid, right? Pretty fast, the fat. So that's lipid oxidation. As water activity increases, right here. Let's go. Browning reactions occur when it's pretty dry, but when it gets really wet, browning reactions, like a Maillard reaction, stops. And that too makes sense to us because if you are frying or grilling or barbecuing a steak or broiling, you're going to get a browning reaction. That's a dry heat. But if we're making a stew or a pot roast, we have a lot of water, then there's no browning or very little browning occurs. So we know that at a water activity of about 6 is where browning occurs, maximum browning occurs. But if we think about food safety and the magic number right here is the FDA number is 8.5. 1 is 100% water. So, oops, 0.85. Too much time on the water, surely. 0.85. That's the magic number. That's the USDA number or the FDA number that says if you have a water activity above that, then it can't be shelf stable. And the reason is because, as you can see, when the water activity increases, the bacteria growth increases dramatically. Yeast and molds don't cause illness. They just make the food bad. So they'll tolerate a little bit of mold growth, but above that. Questions about this? This thing is called a moisture sorption isotherm. But it explains the relationship between water activity and moisture content. Have you seen this thing before? Mm-mm. Mm-mm. So remember that when we're talking about water activity, we're not talking about total water, because water activity can be affected by a lot of different things, like the amount of salt that's in the food, the amount of sugar that's in the food, which would bind the water and make it unavailable. And I'm always harping on, if we change our formulations and decrease the salt and sugar, then we have to realize that the water activity level is going to go up and our food may or may not be shelf stable any longer. Questions about water activity? Okay, so water is also used for heat transfer when we cook, boiling, steaming. Sublimation. Sublimation is freeze drying. So sublimation is the point where it goes from a liquid to a gas without going through a solid state. And that's what happens in a freeze dryer. So if you have a freeze dryer, you make it really, really cold, and then you decrease the pressure, the atmospheric pressure, and that changes the point where the liquid will go directly from a liquid to a gas without going through a solid state. And because that happens, you don't get the crystallization and you don't get the destruction of the food, like you would if you froze it and then evaporated it. That's why freeze-dried food is kind of spongy-like. So that's called the sublimation point. And what it is vacuum or a low pressure lowers the sublimation point. Questions about that? Has anybody ever worked with any freeze drying? Mm-mm.
No, I've never made anything, but we've had some ingredients that have freeze dried, like chives or whatnot, but I've never seen that process.
I'm
Yeah,
currently shopping for a freeze dryer.
you are. Uh-huh. And what are you going to freeze dry in it?
Uh, Ingredients, vegetables, fruits, fermented ingredients.
Hmm. Yeah. And the nice thing out, because it lowers, you lose the water, so you lower the water activity, right? So that it's super safe, and the quality of the vegetable or whatever the ingredient is so much better when it's freeze dried than if you do the traditional air drying, right? And
There,
it's
it does open up, yeah, a whole world of resources that it's flavor wise, stability, and like you said, nutrition are very different than fresh, frozen, or dry. Yep.
yeah, yeah. The only problem with it's expensive.
It's expensive, and there is actually a lot of technique around it. You can't just put it in there and like cross your fingers. There's a lot of like nuance between the different products. I have a friend who has a product that actually does go rancid, so she has to. There's a lot of like freezing first, even before you put it in your freeze dryer. There's a lot of steps to do.
Right.
It's more complicated than one thinks.
Right, right. And so if it does have any fat in it, right, then that because now you have increased exposure to the
Mm,
oxygen, right? Increased rancidity if you have
mm.
fat at all. Um, Greg says in the chat that freeze-dried
Yeah.
kimchi is a great flavoring agent. I bet it would be.
Yeah.
Yeah,
It goes good in everything.
yeah. Um, it's good for you too. So, anyway, so that's called, the jazzy word for that is sublimation. You can impress people with your vocabulary. Another ingredient that we often work with is table salt. So just a little bit about table salt. Table salt is a polar ingredient. This is what the crystalline structure of table salt looks like. And so if you look at it, you'll notice that the chlorine molecules are bigger than the sodium molecules. Yes. So the green is the chlorine and the purple is the sodium. So while we know that table salt is sodium chloride, actually by weight, it's not a 50-50%, right? The chlorine is bigger than the sodium. So actually, it's not a 50-50. You can see up here the difference in the weight of the molecules. So if you're interested in lowering your sodium content, know that it's not directly proportional to how much salt, the lowering of the salt, because the sodium molecule is quite a bit smaller. But you'll notice that these are our handy dandy water molecules with the positive and negative charges. And this is sodium chloride. When sodium chloride or table salt is put into water, it disassociates. So there's some positive molecules and some negative molecules. And it interacts with the water, the positive and negative. So you can go into complete solution until you have too much salt. Then it won't work anymore. But that's what sodium chloride looks like, the crystalline structure. So we add sodium chloride for a flavor. We also add it as a preservative by altering the availability of water in foods, because when the sodium chloride interacts with the water, then the water is not available for the bacteria, right? And that's how come salt lowers the water activity level of the food. So you could have the same amount of water in two different foods, but by changing the amount of salt, sodium chloride that's going to be there, you could change the water activity. Sodium chloride is also used for texture, as a flavor enhancer for savory notes, and a nutrient source, right? Sodium is an essential nutrient, just not too much. It's also a binder in processed meats. It says here that it suppresses flavors such as bitterness. How nice is that? And obviously, as Americans, we like our food salty. At least most of us do, right? So, and it's been relied on way too much in processed foods as for safety. So it's nice to see that people are reducing the amount of sodium that's available, that's in food. And the FDA is busy working on that. The current dietary recommendation is 2,300 milligrams per day. Down from 2,500 milligrams per day. And they're looking to drop it to 2,000 sometime in the future. We'll see. Probably, I haven't heard anything recently. Has anybody heard anything recently about them lowering it further?
Mm-mm.
Good. But they're working on it, because obviously not everybody, but a lot of people are sensitive to sodium in their diet and high blood pressure. So that's why they want us to eat less sodium. But a good way to deal with it is to eat more potassium, because it's a sodium potassium balance. So if you eat more fruits and vegetables, you can balance that out a little bit. And not everybody is sodium sensitive. A lot of people can eat a lot of salt and it doesn't affect their blood pressure at all. So talking about acids, acid, alkali, and pH adjusting ingredients. So an acid is something that produces releases positive ions in the solution, and a base is negative ions. So it's the balance of the positive and negative ions. That's what, and water naturally disassociates, in its liquid state. There's always some free water, hydrogen and hydroxide molecules, but usually they're pretty much in balance. That's why water has a pH of about 7. Unless your water has some calcium in it, like here in California, where we have a high mineral content, and so our water is a little bit basic. So if you add a little bit of acid to that, like some lemon, it changes the pH of the water, and that's why it tastes so much better when it's just, water tastes slightly, in my world, water tastes better when it's slightly acidic. And something off the charts, that alkali water, don't waste your money on that. There's no way you can adjust the pH of your blood by the kind of water you drink, right? Not going to happen. If it did, we'd be in big trouble.
Can you change the pH in your gut with acid reflux,
Mm,
like heartburn?
with
don't
an
know.
with an antacid, yes, but
Gotcha.
with alkaline water, probably not, because the pH of your gut is not on this chart, but it's down here, like lemon juice.
Mm-hmm.
So you really probably couldn't affect it that much. And the
Gotcha.
chances are the more base you put in there, the more acid it would produce to overcome that, right? And
Mhm.
the reason there's acid in your stomach is to protect you from your environment. So if you were to consume a bacteria or something like that, the acid in your stomach would denature the protein. It starts the digestive process. It denatures proteins, but it also protects us against our environment, like if we were to eat something that might be contaminated.
Gotcha.
So the best thing is to eat early, not eat before you go to bed, not overeat in the evening, right? Not too much rich food in the evening. Sleep with your head slightly elevated. All those boring things that nobody wants to do. Okay. So this is an inorganic acid, and this down here, right, this is phosphate. It's an inorganic acid. But most of the all the food acids are what we call organic acids. And that's because they contain this right here. And I showed it to you above as well, but it's often written as this one, like this. This hydrogen disassociates from the carbons and oxygens, and this is what we measure. So organic acids are not as strong as inorganic acids, and but so what we have here are the names, and somebody said learning the names can be a challenge. My suggestion was to make a few little flashcards, those old paper flashcards, and put them around. Like many of you know, I've been learning Hebrew. There's a whole pile of them in the bathroom, right? Next, the kids went to the bathroom. They go, "What are all these little flashcards in your bathroom?" So that's one way to learn things like this. But if we look at them, you probably already know most of these anyway. Citric acid comes from citrus fruits like lemons and oranges, citrus. Tartaric acid comes from grapes and wine, right? Wine, grapes. It's also the acid that's used in baking powder. This one is a little more obscure, malic acid in apples. Lactic acid comes from the word lactose for milk, and acetic acid is vinegar. So if you just look at them a little while, you probably figure it out. So these are the main ones that we use. And each one of these has a different flavor. So if you were adding them to something, citric acid has a different flavor than malic or lactic acid. And then another one is propionic acid. I think it is an inorganic acid. So I'm going to do that. Propionic acid. Oh, it's properties of other fatty acids. It's a fatty acid. Pungent, unpleasant smell. Think we'll stay away from that one. So maybe I should move this all back. Inorganic acids do not contain carbon. The definition of organic is that it contains carbon, right? So
Mhm.
inorganic acids do not contain carbon. So this happens to be phosphoric acid. It's an inorganic acid that we use in carbonated beverages. And you can see that it has a phosphorus molecule in the middle right here. That's what that P is. These are oxygens and hydrogens. And look at all these wandering hydrogens out here. So inorganic acids dissociate more readily than organic acids, so they're stronger, much stronger than organic acids. Some amino acids and some fatty acids are also considered organic acids. Bases are bitter, and we normally don't do a lot with bases except to react with acids because we don't like the flavor of bitter things in general. This is the chemical structure for sodium bicarbonate. So if you've ever made a volcano, right? A kid's volcano, sodium is you add acid and baking soda and you get all that flooding. So this is baking powder, which is sodium bicarbonate and tartaric acid, and it when they react together, it becomes neutral, and we get carbon dioxide and water. So if we add too much baking powder to something, or if we add too much baking soda and we're using acid like an orange juice or an apple juice or something, and we get the balance wrong, it'll taste bitter to us, and that's the sodium bicarbonate if we measure it wrong. Questions about acids so far?
Nope.
No? Good. All right. So if we look at then what is pH, because that's how we measure how acid a aqueous solution is by measuring using a pH meter. So we take a rod that measures the electrical current passing back and forth, a very fine electrical current. And that electrical current will give us the pH. So the pH of acids is low, 0 to 6, and the pH of bases is 8 to 4, and then of course neutral is 7. Most everything that we eat is on the acid side, right? Except for maybe egg white. Egg white is just slightly basic, but all the rest of it is acid. Oh, here's gastric. Here's your stomach right here. So it'd be really hard to affect the pH of that. And
Gotcha.
yeah, and not only that, but this is a logarithmic scale, so each one is 10 times greater than the next one.
Wow.
Yeah. So it's pretty hard to affect the pH of your stomach. So most everything is right in here. And the most important of all of this information is that things with a pH of 4.2 or below are considered shelf stable. So right here. Tomatoes are always iffy because today's tomato aren't nearly as low in pH as they used to be. We're making them, they're growing them sweeter. So there's two numbers that you need to know for shelf stable, and you just need to know these numbers. 0.85 for water activity and 4.2 for pH. These numbers are going to come up a lot. So it's important that you know what those are. And if it's below a water activity of 0.85 and below a pH of 4.2, then it's shelf stable and doesn't need a pressure cooker to package. So that's we look at shelf stable salad dressings and pickles and ketchup and all of those things. questions? When we get to food science, we'll talk about pH versus titration and a little bit about how to take care of your pH meter, because the pH meter is very sensitive. So there are some rules around pH meters, taking care of them. Okay, so an acidulant is something that you add that makes things more acidic. So we could add them for flavor, for antimicrobial, to prevent oxidation or discolorization, protein functionality, and as chelating agents or sequestrants. So if you have something that is going rancid and you want to chelate or sequester some of the trace minerals like iron and zinc, then we can use that. We could use an acid to do that. A buffer is something that can be either or. So buffers are proteins, because some proteins they can be either acid or base, depending on the amino acids that are present there. And so they make really good buffers. And a really good example of that is the albumin, which is the protein that circulates in your blood, very similar to the albumin in an egg. And so, and that's the function of that protein that circulates in your blood, is to keep the pH within a very, very narrow range so that all of the chemical reactions and stuff can occur. So that's what a buffer is. Essentially, a buffer is something that, if it's too acidic, will provide some base to make it neutral. And if it's too basic, will provide some acid. And it just brings the total of the food closer to a neutral pH. That's what a buffer is. Okay, I want to spend just a little time on the if there are no questions about that. Some terminology. Food is a dispersion. A dispersion. A dispersion is something, a solute dissolved in a solvent. And all of food is dispersions. And if we look at that in the terminology, the chemistry terminology, or the food science terminology, a true solution is the smallest. And so that would be something that's totally dissolved, like salt or sugar. Most food is a colloidal solution. That is, it's either a sol, a gel, an emulsion, a solid emulsion, a foam, or a solid foam. And it's so that is the intermediate. And then a suspension is the largest ones. And so a suspension is something where it falls out, where the particles that are dissolved are so big that they fall out. And we see that if we make a cornstarch slurry and you mix it all together and then you let it sit and then the cornstarch falls out. That is a suspension. It was suspended, and now it is not. And it's all based on the particle size. So the smallest ones are true solutions. The intermediate ones are the colloidal solutions. And finally, there's the suspensions, which are the biggest ones. If it's a colloidal solution and it pours, we call it a sol. So that might be something, ketchup maybe might be an example of that. Something that pours, or it might be a gum, something that we've made as a gum, and then we can pour it. A gel is a colloidal solution that does not pour, like a jam or a jelly. An emulsion is two immiscible liquids and an emulsifier. And a solid emulsion is a liquid in a solid like butter. A foam is a colloidal solution, and so is a solid foam like a meringue. So there's just some vocabulary. So why is a foam a colloidal dispersion? Because it's a gas bubble dispersed in a liquid. Right? So if you whip up egg white, right, you've got the protein that's surrounding the air bubbles, and then you've got the water and all the other stuff in between. That's a foam. And for mouthfeel, creaminess depends on particle size, and viscosity depends on the liquid. So if your foam is too runny, if you add a gum, right, to the liquid, and then you whip it up, then it'll be more viscous. It'll pour. It won't be less runny. I don't know. Anyway, foam stabilizers are gums, sugar, acid, fat. Foam suppressors are liquids, phospholipids, which are emulsifiers, small muscle surfactants, and salts. So I looked this all up in the Essentials for Food Science, so if any of this is important to you. And then egg white foams, right? So we all know that if you want to make an egg white, egg whites are whipped warm, right? And cream is whipped cold, right? Cream cold, whites warm to get maximum. This is what whipped cream looks like. That's kind of cool. Huh? I don't know. Questions about any of this? Is any of this relevant to what you guys do?
Yeah, I was
Yeah.
going to say that the acids are very relevant in testing the pH of finished salads. We tend, right, to go for a lower pH if the flavor profile will allow it, because we know we'll get a better shelf life.
Yes.
Hmm. The emulsifiers are important for me in developing batters.
Okay. Which emulsifiers do you use?
Oh, well, we use gums typically, like guar gum, xanthan gum. In Arabic, and I'm drawing a blank, but we've got quite a few.
Okay. So the gums,
Bells.
yeah. So Greg, the gums, the way I understand it, and maybe I'm wrong, is they're not exactly the emulsifier, but what they do is they thicken up the watery part, the vinegar
Okay.
or the watery part, so you get a more stable emulsion. But they themselves are not the emulsifier.
Okay. Well, then emulsifier for me is eggs.
A great one, may I say.
Hmm.
How about some of you other guys? What do you use? Do you use any make any emulsions?
I don't make emulsions, but we use a lot of mayonnaise. So we use gums as well, like a mix of xanthan and guar to kind of like capture any free water that might leach out of vegetables. We'll use like modified food starches in products like lobster salad, or we'll use starches in quiche to help keep the eggs from like overcooking and coagulating, and keeping like a nice mix between the eggs and dairy.
Oh yeah, yeah. So the starch in a quiche, I think, would keep the egg from over coagulating and getting tough, right?
Yeah.
Yeah. Kind of breaks it up, right? Yeah, and then think about the salads and stuff, but certainly as the vegetables age and break down, right, they release a lot of water, right?
Yeah, and we tend to use a lot of like ready to eat IQF vegetables, so they go in the mix frozen. So you almost have to expect and plan for their release of water. And yeah, we have a couple gum blends that work really well to kind of capture that, so you don't have any pooling in your containers and retail shelves.
Yeah. And do you know that gums do not affect water activity, right? So
Okay.
they may capture the water, but that water is still available for microbial growth. So they do not affect, the way I understand it, they do not affect water activity. You might
Okay.
think that it is because it's thicker, but not necessarily.
Okay.
Yeah.
Good to know.
Yeah. Anybody else? Any other?
Nope.
No.
There were some gum and emulsifier blends that we used years ago in like airline meals that we did um in meatloaf and meatball applications. So the emulsifiers would like suck up all the fats instead of purging out and into like boiling bags. It would just keep it inside the meatloaf.
Oh,
And actually, we use something on frozen vegetables also in airline meals. Um, so when they would reheat these meals, you wouldn't have a pool of purged water sitting in the bottom of the tray.
yeah. And think about after they've murdered your food, right? In one of those oven things, held it there for way too long at way too high a temperature.
Yeah.
They decided there was turbulence and they weren't going to serve any dinner for an hour, right? Or whatever. So, yeah. I always feel bad about airline food. Everybody always gives it such a bad rap, and I think it's pretty amazing that it tastes as good as it does.
If it we did, we're in Atlanta. This was my last job though, but I mean, when everyone we had accounts with, um, the American Airlines were really bad, sort of like what everyone thinks of. But then we had a lot of like Korean Air, Emirates, Qatar, most of the European airlines put a lot more of your ticket price into the food. And so there were some really, really nice meals.
Hmm.
Quality was a lot better.
Yes. I always do prefer to fly one of the foreign airlines. Right. Good point. Right. Good point. So there are hundreds and hundreds of different additives. And we just need to know kind of an overview. Next week we'll talk about a few more. See if I can be a little more entertaining maybe next week. Okay, I have run out of stuff to talk about. Do you guys have any last minute questions or concerns?
Nope.
Yes, go away, Jill. Okay.